Good morning and welcome to today's global webinar. We're excited to have Cam Morris, who's the project leader for OWASP Passfault, with us, and Cam is going to take us through a slide deck. And please, if you have any questions during the webinar, go ahead and type them in the question box or the chat window, and we'll make sure Cam gets them. So without further ado, I will turn things over to Cam.
Hello, thank you. I'm really excited to show this. This is a project I've been working on for quite a while, and a little introduction on myself here. Let's go to this slide. So I work right now at Department of Defense contractor as a software security specialist, which means I get to be a developer 50% of the time and worry about security and security training the rest of the time, and I really enjoy that mix. I think it's fun to get into the code and also take care of the security. So this project, it's a solution for analyzing passwords, but it's more than that. I'd like more than anything for people to come away as this could be a password policy replacement. And that's my hope. We're going to talk not so much about why, because I believe that most of the people on this conference, watching this, are familiar with the pitfalls and the bad things that can happen with password policies. I have here on some of these examples the XKCD example, that cartoon, that comic strip here. I'm sure everybody's seen this. This explains really well the pitfalls of passwords and password policies, and how password policies really are not, they're doing more damage than good, really. So let's go forward a little bit. So I'm going to skip over some of these reasons why password policies and passwords are struggling, and how I feel that Passfault can help address some of these. So one of the things is, why don't we measure the password strength in these password policies? And part of that is we don't really have a good way to measure password strength. Instead, we've been relying on these guidance of uppercase character, or uppercase, a mix of uppercase, lowercase, special characters, numbers, and that really doesn't work. So this is how Passfault works. First, we identify the patterns that we can find in the password. Each pattern is measured for its size. And by size, I mean how many passwords fit in that pattern. And then you find the weakest combination of all those passwords. Then we come up with an estimated time to crack. Really, the combination of the pattern size is the real measure of the password strength, but this estimate time to crack is more for the layperson, because when you start talking about quintillion number of passwords, they don't really have a meaning, a good intuitive feel for how large of a password that is. And then finally, we tie that estimation of, not necessarily the estimation, but then we tie that strength to your password policy. So more in detail, you identify the patterns, and we have a whole bunch of really cool pattern matchers, and we keep getting better as we go along. Different dictionary words. We look for dates. We look for leet speak. So if you've got leet speaks substitution in there, it'll pick up on that. If you've got keyboard sequences, which are actually really weak. You have a sequence of ASDF or QWERTY. Those are keyboard patterns where you just put everything in a row on the keyboard, and there's only a very limited number of those available, so they're really weak, but they're really easy to remember and easy to type. So We got misspelled words, which is, I think, a novel thing. I don't think I've seen that anywhere else. We got dates, we got backwards words, all kinds of patterns that we can look for. So the next step is we measure the pattern size. And this is how many passwords fit in that pattern. I think this is a much more accurate, more meaningful. A lot of password analysis, like how big is my password and password haystacks, you'll see measure the randomness of it. So they measure uppercase, lowercase, special characters, and how many passwords would fit in that pattern. But there's much more patterns than just random. So if you took away all the pattern matching of Passfault and just left random, then you would be equivalent with these entropy-based password evaluation that you see out there, like how big is my password haystacks. But I love the idea of password haystacks, at least in the concept of it's a needle in the haystack. How big is your haystack? Each of these patterns that we find is measuring how large the haystack is. So random is a really large haystack. If you're using dictionary words, that haystack gets a lot smaller. And I wanted to throw in a little thing here. We always talk about in security the obscurity versus security. Password pattern size, if it's large, that is more security than obscurity. But if you have an obscure pattern, like a word spelled backwards, it might be really obscure in that people probably, like crackers, probably don't do a lot of backwards words, but the size of it is not large. If they knew that was your pattern, it would be really easy to crack. So at this point, I'd ask if any questions on the pattern size, on how we find patterns and what the pattern size is. But I'm going to, as I don't have much interaction here with the crowd. So when we find all these patterns, we find a whole lot more than what actually fits. You can only have so many patterns chained together. So we go through in kind of like a knapsack. It's a knapsack type problem of how can you fit the most in your knapsack. So we go through all of the different combinations of patterns and find the weakest combination. So we're trying to estimate the worst case scenario when a hacker knows what kind of password pattern you've used. So if you've used an English word, one of the U.S. cities, that's one of our dictionaries we use. If you use a Spanish word, you chain all those three together. Worst case scenario is the hacker knows you've used a Spanish word, a U.S. city name, and an English word. How long would it take? What's the size of passwords that fit in that pattern of those three patterns combined? Then we estimate the time to crack. Now, this can vary. It depends on how you protect your passwords. If you're using the old school, 1 or 2 rounds of SHA-1 or MD5, then this estimate time to crack is going to be really quick. So the time to crack depends on the system that's protecting your password. It also depends on what kind of hardware you're using to crack the password. This is assuming an offline attack where you have the hashes from the database already downloaded, and that helps us estimate your time to crack. And this is where a password policy makes a lot more sense, because if you know what type of password hash you have, and you can estimate what kind of attacker you're going to have attack you, then you can come up with your own risk analysis, and that, I think, is really powerful. So another thing is it gives an intuitive feel for the user. It enables a self-training, and this was, I had kind of suspended work on Passfault for about a year, almost 6 months ago, And then I showed this to my father-in-law. He asked me, he said, hey, you're a security guy. Can you give me some advice on passwords? And I was like, oh, let me tell you. I could go on for an hour. But instead, I gave him kind of the quick elevator pitch of what this project was, and I showed it to him. He played on that for an hour. And he's a foot doctor. So I thought, hey, I got a foot doctor. And he was playing it like a game. He'd come back to me every 10 minutes like, hey, look at this password. This password is, this can be cracked in 10 centuries. Isn't that amazing? Then you come back, I got a 100-century password. So I think this is exciting in that it enables a self-training. People learn quickly what a good, strong password is. So, oh, I already mentioned this before. We could tie this to the policy, and I think this gives the administrator a better feel for how the strength of his password is across the, not his password, but across his organization. I think it gives you a better chance to manage password risk. So I'm going to do a quick demonstration here. Let's come over to my browser, and so here's the GitHub project. And here is the demonstration website. I'm piggybacking on Google's App Engine. So here we got passfault.appspot.com. Notice I put the HTTPS because it's this password does go over to the server on the back end. And that is probably the most frequent question I get is what do we do with the passwords? Is it done locally? There are some things we can do to analyze the password locally. We have an applet, and we also want to do some more work to compile this down to JavaScript so it could all run locally that way. So if there's anybody out there that has good experience with Google's Web Toolkit, I've been looking at it, and I'm not kind of a novice on it, and I'd like some help in getting this compiled to JavaScript. I think a lot of people would use this more if this were a JavaScript library. So here we got some examples. Here, let me increase the font so you can see this. Here's some weak passwords that pass typical policies. You've got your really long password that has uppercase, lowercase, numbers, and special characters. And yet this is weak because this is just a password pattern. So if you held down your hand over QWER and then held down the shift key and did it again, raise your hand up to the numbers and did 1, 2, 3, 4, held the shift key down and did 1, 2, 3, 4 again. Really easy to remember. Like I mentioned before, we contract to the Department of Defense for all of the accounts that are not smart card enabled. They have their CAC cards. Then they require a 16-character password. Well, hey, here's a 16-character password, and it's probably the weakest ever. So this first time it'll analyze. It takes a bit longer on App Engine because they heavily restrict your multi-threading access. So here you see the results. It says this password needs more strength. The number of passwords in this combined pattern is 8 billion, which sounds kind of big, but not with today's cracking, and not with, certainly not with old school type password hashing. So here you'll see it found 4 patterns. They're all horizontal keyboard patterns, and they give you a little bit of information of how much that pattern contributes to the overall strength of your password. And if you want some more detail on each pattern, you can hover over it and see, this was QWER. There's only 296 passwords in this pattern, not very strong. And you're maybe wondering, how do I get 200? How do I go from 296 to billions? And essentially what you have to do is these numbers are multiplied. So I have 286 or 96 times 296 times 296 times 296. And that's where you come up with 8 billion. So at this point, I'm going to jump over to GitHub. So here's our GitHub. Come over to here. Here's your URL to clone. And when you come down to Get, here is the project that you'd get. The core library is a Java library. For those that don't want to need access to this without Java, I built this JSON service. And this JSON service is pretty much identical to that website I just showed you. So let's step into that. And I'm going to run it. I just upgraded to Gradle, and it's fantastic. I love the build system. I think this will help people jump in, contribute. You'll also notice that there is an applet for this. So if you did want to run this locally, there's the build for the applet. They're all published out to Maven Central. So here it's running. We can come back over to our server. So if you don't want to send your passwords over to Google's App Engine, clone the repository, build it. You saw it wasn't all that difficult. The first time it'll take a while to download some the web container Jetty. It'll be on localhost 8080. Here we go. That will point you to the right location. So we'll go through the rest of these examples. Going to localhost. You'll see it's a first time it takes to load. It takes a second, but after that it's a lot quicker. So, and this isn't so much the network as it is the multi-threading capability. On Google App Engine, they don't let you create and hold on to threads, so I have to create a whole bunch of threads on each request. So it's almost as fast as if I just analyze them sequentially, but that's a bit too much into the details. So let's come back. So here, another typical password that would pass your normal policy. You got a dictionary word, a number, a special character. Again, this would take less than a day to crack. The passwords in this pattern are 822 million. Most of the strength comes from the dictionary word. One of the features that I'm working on that I was really hoping to demo today, but I didn't get it completely done, but it'll be in the next release, which should be out soon, is you'll see a lot of the accuracy here depends on the word list. Some words are used a lot more frequently than others. So what we've done is I've got a frequency word list so that we have the most frequent words that end up being the smallest set of words will be first and give them the higher priority. So we'll be getting a lot better accuracy out of our password analysis in the next. So some passwords that typically fail your normal policies, like completely, I believe this is 16 characters, but the problem here is it has no special characters, it has no numbers, it has no uppercase. How can that possibly be secure? Well, that's a lot of patterns, a lot of passwords in this pattern of 16 completely random lowercase characters. So if we look at the detail here, you'll see that it found Latin characters and that it did not find any uppercase or numbers. And so it is smart enough to determine that if I were to put in some numbers, let's say if I took half of these out and just put in numbers, it's smart enough to realize that the numbers are all grouped together, and we'll treat those as different passwords. Oh, I did horizontal. Bad habit. Okay, so I got to get a random number, not horizontal keyboard number. So here you'll see it determined two random characters, one that was all Latin characters and the others that was numbers. So that, you'll see, even though it's about the same length, it lowered the strength of it. Another pattern that I think a lot of people would like to use are passphrases, but they can't because most password policies prevent that. So here you'll see we have a U.S. city in this password, Seattle, a smaller English word that comes from the tiny lower dictionary. We have two of those, and then a Spanish word. The total number of passwords in this pattern is 1 quintillion. I'm not exactly sure what a quintillion is. I had to look them all up in Wikipedia to get past a trillion. But and I don't think our users will either. And so that's really where this 2 years, 1 month is important. It's that estimated time to crack. So maybe we should talk some more about that. So here, under these show options, we've got crack hardware and password protection. So right now the default is Windows NT LAN Manager. If we wanted to upgrade that to, say, bcrypt or WPA or Microsoft Windows NTLM2, I took all of the cracking speeds from Hashcat, one of the GPU cracking accelerator projects that I've been following. So let's go to SHA-512. Let's say it's been hashed 100,000 times. And that would take on an average computer probably about a second to go through that many rounds of hashing. So it adds a lot of latency. So let's reanalyze this. And same size of pattern, but you'll see it takes a lot more centuries to crack this. So that's on an everyday computer. And there I'm assuming that there's one GPU to use. So we have some other profiles of different types of hackers. And a dedicated cracker is what I'm calling a $5,000 machine, which I'm assuming a GPU will cost around $1,000, so it's 5 GPUs. Organized crime cracker will have $50,000 of $1,000 GPU crackers. So let's go all the way up to a government cracker, which I assume they'll $1,000 towards making a password cracker. Maybe I'm not giving them enough credit. Maybe I'm giving them too much credit. Who knows? So that took down the centuries from hundreds of centuries down to a decent number of centuries. If we change this back to, say, WPA hashing, which doesn't do as many rounds, it cuts it down to 1 century. If we were to go back to old school hashing, just one time, that cuts it down to 4 months, 4.5 months. So even though that's a pretty good password, your password protection makes it weaker. And I think this is, let's go to the password policy. This is exciting from the policy standpoint because your password policy now, instead of trying to guess how many uppercase, how many lowercase, how many repeated, how long do I want my password to be, you have this estimate of here. You can tell your password policy how you protect it. Let's say you protect it with 100,000 times of SHA-512. And when you're cracking your password, let's say you're a bank and you don't want China getting in, so you assume they have a really expensive password cracker. So password pattern size of 100, let's say we come out here, size of 700 billion. that password could be cracked in 7 days. So that might not fit your risk. Let's say that in your risk analysis, let's say you assume that it'll take about worst case, it takes a month to determine that your passwords got dumped from your database. So you want at least a month. You probably want another month for your users to be able to reset their passwords. So let's bump this up to 2.5 months. Then your password policy is really 5 trillion patterns in their password. So the exciting thing about this is it's simple. It's really intuitive to see what your password policy is. I think it's there's a lot of power in simplicity, and so I'm excited to see, because I don't know if I want to get into predicting the future on passwords, but people have predicted passwords dying for, gosh, almost 2 decades now, and it doesn't seem to be going away. I'm excited about all the other things. I love my CAT card. I love my 2-factor authentication on Google, but gosh, passwords are here to stay for the foreseeable future. So I'm hoping to give some protection around it. So let's go back to the presentation. So here's kind of my marketing elevator pitch here. I think we've got something that is more accurate, more simple, more informative, and more powerful than what we've got. So I'm going to zip through these. Oh, and password advice. After spending all this time, is there any change? I'd change this 12 random characters. Actually, 12 random characters I think would be good, but 16 characters has become the length standard, really. 4 random words are great. Misspelled words are really hard to enumerate. It really adds a lot of entropy to your password, so I recommend it. So if you're a bad speller, that's finally good for you. It helps to be a bad speller when making passwords. Okay, some of the things that we want to do next. Let me show you real quick this project. Let me check the time. Oh, good. We got a good time to talk some more. Maybe now would be a good time to open up some questions, and then I could get to some what next after that. I should probably look over at my webinar. Let's see if questions have already been posted. Okay, I'll come back and check that in a bit. And in the meantime, I'll show you some of the other stuff that we have. So we're going to come out of the JSON service. I mentioned the applet. The App Engine project extends this JSON service. And the JSON service is really what I would say is the example to follow. I could show you the code really quick. Here is the servlet itself. The analysis isn't all that complex. I've tried to hide all the details of complicated details that aren't really necessary to know. So here we are collecting the password over a post. The password doesn't get put in headers. I have it in a secure string, which is just a byte array so that I can clear it, because Java has a tendency to hold on to strings, and we don't want anyone to be able to dump the memory at Google and get these passwords. So as soon as it's done analyzing, it'll clear out that password, clear out the memory. So here we get the password from the input stream. I don't have any I don't use any of the extra features to parse parameters because I don't want them into strings again. So I just read it straight from the input stream. I build my finder. It's a composite finder because it's combining all of the different pattern finders into a multi-threaded finder. So I pass the password into this password analysis. The password analysis holds the result of the analysis. Here we analyze the password. We wait for that to complete because it is non-blocking. Then all the results will be stored in this analysis thing. We write the analysis out in JSON so that any clients can use it, and then we're done. This JSON service has become kind of the example to follow. Here I have a little password form, the analyze button. Here, so here you'll see this submit password. When that button is clicked, it will submit the password and look for the password ID. It'd be nice to pull this into a nice plugin. I think that's another next step. So the submit password is fairly simple. Here you'll see my code for applets. So it will check to see if the applet is present. Well, here I just have a simple flag of applet equals false. If the applet is present, then it will call into that applet and analyze it. The applet also returns JSON, so I can use the same code. It's turned off right now because it had so many people wanting to be able to access the site over, with their iPhone or tablet. So here we make this AJAX request over post. The URL here, when it comes back, we take the JSON that's sent back and we apply this template. So it just templates all of the JSON response into a web page, and that's it. So I would like to make this a little easier to use if you're a web developer, to make a nice JSON, a JavaScript plugin, probably a jQuery plugin. But you'll see it's not that complex to get using. Another thing that I'd be really excited to do as far as the next step, if you, I mentioned the GWT compiling the Java code into JavaScript. That would make it even easier for web developers to grab this and use it. And I love the idea of having this all analyzed on the client and not have to worry about it going over and having someone grab your password. So let me have in the core library, I have a built-in command line interface. So if we say Java, it's built in the build libs Passfault core. So if we run that command, oh, my Passfault thing got a little squished. That's all right. So we enter in a password. Let's say we enter in security, a keyboard pattern, and let's do a elite. So that would be a 7. Let's put in a 1 here so we have elite speak. And then we get to pick what kind of attack profile and protection profile we have. Let's say we got a high-end government cracker, and let's say we've chosen to select protect this with bcrypt. So here you'll find that instead it found the numbers pattern because 1337 is smaller than a dictionary with lead substitution. So it found both of those patterns and it chose the random numbers instead because that was a smaller pattern. So if we were to enter that same thing again, security, and instead I had so I have a mix of real characters in with I'm typing and not talking. Okay. Oh, interesting. It's interesting to find the different patterns it finds. Sometimes it doesn't match the pattern that you used to create it because it found a weaker pattern. So what I was getting at with this command line is it's pretty basic. It's just kind of a proof of concept. I'd really like to get a command line that could plug into Linux. I'd love to have a Linux administrator just be able to grab this in their with their yum or RPM or whatever package management they're familiar with and have it come down, set a quick policy, probably have a reasonable policy by default, and then every time someone enters password to change their password, it would run this to analyze the policy and enforce the policy, or analyze the password and enforce the policy. So if there are some Linux guys out there that could help me, I've done a little poking around. I know that you'd probably tell me that I'd have to do something with a PAM module, and I'd probably respond with something like, Pam, yeah, you should go talk to her. That'd be great. So if you can help out there, that would be great. I would be excited. Another thing that I'm excited about are the words, the word lists. That plays a key role because the size of the dictionary is the size of the pattern. So I want more meaningful dictionaries. So what I've done currently, with the help of some students from the University of Florida, we put together some passwords or word lists for first names, U.S. first names that came from the Social Security database, which is public domain. We also analyzed the last names from the U.S. Census and then organized them in the least frequently used and the most frequently used and group those into percentiles. So we have like 68th percentile, and that's a really small list, but it covers the most of the population. So it would be the most likely to appear in the password. So those will have a smaller strength because they're more frequently used. We've also done the same thing with English words. What we did is we used the closed captioning for movies. There's an open project, and somebody went and created a frequency list out of those. So we pulled those in, and that will be, all these will be in the next release, which I'm hoping to release in the next week or so. However, there's not much I've done internationally. I've done some proof of concept things. We've got a Russian keyboard to make sure that that's international. So another thing that people could do is they could create similar frequency lists for different languages. Russian, we have a keyboard for it. We can put in keyboards for different locales also. So that'd be a great way to help if you're not too excited about getting into the code. So I'm going to come back over and see if we have questions. I don't see any. We are planning on rebroadcasting this later tonight. So if you have questions, you can send them my way. I have a mailing list for this project that you can get from the website. Let's see, from the OWASP project page for Passfault. Also here I have a list on the open source button. Oh, looks like I lost my network. Oh, no, that's not true. This is my local page. Regardless, you get the idea. We have a mailing list, or you can send an email straight to me. My OWASP email address is cam.morris@owasp.org. So you can send me questions there, and I'm hoping that we can get some real-world implementations. If you're excited about grabbing this and using this in your product, I'd love to talk to you and see how it goes. And the goal is to get this towards a stable release, and I think we're getting there. We're getting close. So I think that is all I have to show.
Okay. Thanks, Cam. Are there any questions from the audience for Cam? He did provide his contact information, so if you think of something later, feel free to reach out to him. And if you joined us late, and know a couple of people did, that's fine. This webinar has been recorded and will be posted on the OWASP YouTube channel, so you can review it and read up and still reach out to Cam. So if there are no questions, I'd like to thank Cam for his time today. I know this is a pretty exciting project, and you're looking for some support, some input, some feedback, helping to get things moving. So if there are no other questions, then I guess that's it. Thanks for joining.
Thank you.